So please join me in welcoming Zach Weber. He is an associate professor of philosophy at the University of Otago, where he works on philosophical logic. He has very generously agreed to come speak with us more about his work on paraconsistency. So welcome, Zach.
Thank you very much, Sebastian. It's a pleasure to be with you this morning, or it's morning here in New Zealand. It's Saturday morning. Yeah, it's great. I just wanted to share on a personal note. I lived in Ohio when I was a little kid, so it's nice to be zooming into Ohio to talk to you guys about this. All right, so my topic this morning is on my main area of research. The title is On Paraconsistency, Moderate and Radical Approaches. Just to give it away, I'm going to be focusing heavily on the radical approaches, as I'll talk about what that means, but comparing it to the more moderate approaches and trying to very honestly show up the pros and cons of it to forecast. I'm going to say that the radical approach is the philosophically better one, but it's much technically harder and open-ended and woolly and scary and dangerous. And the moderate approach is probably what you should do if you want to finish your degree. So let's get into it. I'm going to situate the discussion. Paraconsistency is a broad thing. So to focus down a little bit, I'm going to focus on an area called inconsistent mathematics, or sometimes it's called paraconsistent mathematics. There's a little Cambridge Element that came out last year, edited by Stuart Shapiro, that I did on paraconsistency in mathematics. So that's what this is. What is it? It's a branch of mathematics using non-classical logic, and all it takes to be a paraconsistent logic is to invalidate explosion. So you need to have a background paraconsistent consequence relation where an arbitrary contradiction, A and not A, does not automatically give you arbitrary B. That's all it takes. Paraconsistency is a negative thesis. It doesn't really say anything positive at all. It just says ex falso quod libet, or explosion is invalid. And beyond that, it's up to you. So I don't want to just spend an hour shouting into my laptop. So just to pause right there, that's everybody's knows what paraconsistency is, more or less. All right, so that's what it is, and the idea is to apply it specifically to studying mathematical theories. And that was what it was intended for, really, from almost its inception. The first paraconsistent logic was probably Jaskowski in Poland in 1948, but in the 1950s, particularly in Argentina and Brazil, people like Florencio Asenio and Newton da Costa pioneered paraconsistent applications to mathematics mostly for set theory and arithmetic. Arruda, well, this is A.I. Arruda. She was a student of da Costa who worked with him on set theory in the 60s and 70s. She discovered in the 70s that da Costa's first proposal for a paraconsistent set theory was trivial, and told him so, and he had to go back and revise things. That always just really impresses me, that a young woman working with this very eminent sort of mathematician, as his student, was able to tell him that his work was basically completely flawed and needed to be redone. She unfortunately died relatively young in the late 1980s, so I would have liked to know what she would have come up with if she had stuck around. She did some early pioneering work on paraconsistency that I find very inspiring for its bravery. I'm the host, so I'm going to mute Robert. Okay. Yeah. In the 1980s, it gets picked up. In the 70s and 80s, it gets picked up in the Australasian tradition, which is what I studied. So I originally moved to Australia to study with Graham Priest. So people like Priest, who's pictured there in a cartoon, and Chris Mortensen and Robert Meyer developed models of inconsistent arithmetic. People like Mike Dunn. And then Priest has produced models of LP set theory, as well as his student, and then my co-supervisor, Greg Restall. And then it's been continued to be applied to things like calculus by Mortensen and Brown and Priest. And into this century, Mortensen has continued to use paraconsistent logic to study things like inconsistent geometry. He has a book from 2011 on that. And in the last 10 or 15 years, there's been further developments, particularly in relevant set theory and real analysis, and pushing things further into meta theory. This is not to overstate the case. This is work done by a pretty small group of dedicated people, and there's baby steps forward, but still lots to be done. So that's just to convince you that the field does exist. So there's different approaches to paraconsistency, right? You're interested in some sense in theories that might be inconsistent. So you're going to use a background logic that can tolerate inconsistencies. But there might be a lot of different reasons you do that. And the main style of approach is what we'll call moderate, which just aims to take kind of classical theory or classical logic and extend it. It's as if the classical theory is a little bit like Newtonian physics, where it basically works for small, medium-sized goods. It's just when you get out into the vast reaches of interstellar space, you start to need like Einsteinian relativity, but it basically doesn't usually come up until you get out into the transconsistent. So you might also say transconsistent analogous to the transfinite, like the rules change as you go up the hierarchy, but mostly down here, everything stays the same. So motivations for that might be because you think that ex falso quod libet is a bad rule, because there might be inconsistency in thought or language or belief, or maybe if you're feeling brave, you think that there might be other possible worlds that are inconsistent, but you don't think that this world is inconsistent, and you think that consistency-based science and mathematics is basically reliable and correct. And if a theory is going to be respectable, it ultimately needs to have a classical representation at the end of the day. There has to be some kind of model in standard classical model theory that corroborates that the theory you're working on is coherent, like a non-triviality proof or a consistency proof. The more radical end of the spectrum is more revisionary. So what I just said is not revisionary at all. It doesn't go back and say that there's anything really wrong with classical logic or classical practice. The more radical view says things like, well, we should deny ex falso quod libet because the consistency hypothesis has failed. So this is how Richard Routley and Robert Meyer put it in the 70s. The hypothesis that the world is consistent has been demonstrably demolished, and we should give it up and rehabilitate and reconsider all the theories on a paraconsistent basis, which means that some of the classical ones are wrong and should be rejected. Kind of along the lines that I think Brouwer thought that, things that were proved with the law of excluded middle were wrong and shouldn't be done. And there were more moderate kinds of constructivism that were developed later by Bishop that kind of fit in nicely within classical practice, but that wasn't the intention originally with the intuitionists. And I think that wasn't really the intention originally with the, at least Australasian paraconsistentists, that maybe even when we reject the old stuff, there could be new theories that aren't even representable by the old classical methods, at least not faithfully. So in this talk, I'll be comparing these a bit, but I basically want to explore and extend the more radical end of the spectrum, where there are truth-value gluts, or the word is dialetheas, which means true contradictions, and that word was coined by Priest and Routley in the 80s. I think they were originally calling it dialectics, thinking of Hegel, but thought that it needed a new word. And we see these two kinds of tendencies, the more moderate and the more radical, reflected in different quotes from pioneering researchers in the field. So Da Costa just says, look, it would just be as interesting to study inconsistent systems as it might be to study non-Euclidean geometry. And it doesn't mean you're committed to some non-Euclidean geometry being true, you just think it's interesting. Whereas Meyer says things like, what is to be hoped for most of all are not new roots to old truths, but an expansion of the pragmatic imagination. And that's what I hope to do a little bit of today, is to expand our pragmatic imaginations. By the way, there's only a few of us here today, and we have a long session, so I don't mind at all if people want to interrupt to ask just clarificatory questions or anything like that if it goes by too quick. If you want to ask a long objecting question, we can save that for the Q&A. All right, so my aim today is to evaluate the philosophical and technical tenability of the radical approach. I'm going to argue that if you think there's any good reason to use a glutty theory, so a theory with true contradictions in it, in some sense, then you should also think that the theory you use to study that theory, the meta theory, should be glutty too, that it doesn't make any sense to accept true contradictions at an object level, but then try to maintain consistency at the meta level. That if you do that, you run into serious philosophical problems, and that we should be looking at paraconsistency all the way up, which also runs into problems, but that's what we'll be looking at. So the issue is really how to go about doing that. And to some extent, I'm citing myself here. I'm extending and developing some work that was in my main monograph from a couple of years ago, Paradoxes and Inconsistent Mathematics. This talk is written up as a paper that is undergoing final revisions. So if, as we're going along, if you do spot anything, there's still time to fix it up. Maybe. All right, so I'm just sitting here blithely talking about true contradictions, like true contradictions in the world, and I didn't even really try to soften you up about that. The sincere kind of question that maybe has crossed your mind that I get all the time, got it yesterday from a good student who said, look, maybe thought or language could be inconsistent. In fact, that's pretty plausible. But look, obviously the world and the truths about the world are consistent, right? Like this tree is out the window and the sun doesn't fall out of the sky. What would a radically paraconsistent thing even supposed to look like? What are you talking about? Nodding. So I'm going to sketch a response to this. And to respond to this kind of objection, I want to put forward two hypotheses. One of them I call the ordinariness hypothesis, which is just roughly, if you say, what does a paraconsistent tree look like? It looks like a tree. It looks like a tree that you use a paraconsistent language to describe and a paraconsistent logic to theorize about, but the thing itself that you're talking about is just the ordinary objects of our everyday experience, like trees, or in mathematics, it would be set theory and arithmetic and analysis and topology and all just the usual stuff. It's not a different object with sort of macabre or esoteric behaviors. It's the same object theorized with a different logic. So the slogan here is to expect the expected, right? A paraconsistent table should just be a table. At the moment, I have a project where we're working on paraconsistent computability theory, where we're supposed to be thinking about what would a paraconsistent Turing machine look like, which hopefully at the end I'll have a moment or two to say something about. And the idea there is like if a Turing machine has a tape or something, the paraconsistent version isn't where we twist the tape into a Mobius strip or send it through a portal to another dimension or with dragons or something. It's just a tape with a read-write head that goes back and forth on it. It's just that the logic it's running on and that you use to think about it is inconsistency tolerant. So we'll expect the expected. On the other hand, we should also take seriously the non-classicality is non-classical hypothesis, which is once we go back and theorize our ordinary everyday objects with the paraconsistent logic, we might get different results than the classical theory. The non-classical theory could and maybe should lead to different places than the classical one. It would be sort of weird or a waste of time to recast everything in a non-classical logic and then get back out exactly what we already had from the classical theory. So the things that we think of as the standard theories are relative to classical logic. They've been developed, especially in the 20th century, by classical logic. And when conventional concepts and definitions and proofs and theorems are expressed paraconsistently and established using only paraconsistently valid arguments, one can expect divergence from the classical case. So it's ordinary, but can diverge. So we should also expect the unexpected. So put these two things together. The ordinariness hypothesis says, expect the expected with respect to our experience, but non-classicality says you should expect the unexpected with respect to classical theories. And hopefully between these two things, we'll find some kind of balance, right? If you go too far one way, you take out your other countervailing hypothesis and pull yourself back and find some spot in the middle is the hope. So a paraconsistent table is just an unsurprising table, and that itself is kind of surprising. All right, so we're still warming things up here. So according to truth-glut theory or dialethism, there are propositions that are both true and false. So some proposition P that has a true negation. That means P is true simplicator, like true, not true just in a model, it's true in the world, whatever that means. Why think this? So I'm not going to give the whole argument here. Hopefully at some point your group will look at some of the arguments to think this, but the basic thought is that accepting true contradictions provides some kind of direct resolution for the famous paradoxes in logic and mathematics that came to the fore, especially at the beginning of the 20th century, and culminated with the demise of Hilbert's program around 1931 and the discovery of uncomputable objects in the mid-1930s. This is the self-referential fixed point phenomenon that underlie the famous limitive theorems like Tarski's theorem that you can't have a truth predicate in a language, or Gödel's theorem. So one reason the solution is appealing is because all the other solutions run into some kind of revenge, and revenge is a technical term. All the approaches to the paradoxes that try to find some other way around seem to put forward protocol statements that they themselves then have to violate or contradict somewhere down the line. So you say something like, no proposition can refer to all propositions. There's no way to universally quantify. And then you stop and think and say, wait a minute, the proposition I just said seems to refer to all propositions. And that just happens over and over and over again. You try to introduce like, well, maybe some things are meaningless, and you get a revenge liar that says, all right, well, then this sentence is either false or meaningless. Any kind of way to, if you like, to put it poetically, any way to try to outrun the horizon just catches up with you the next step along, or else you just need to go terminally silent like Wittgenstein at the end of the Tractatus, where first he contradicts himself and then just stops. So the dialethic approach does contradict itself. It says, look, there are some true contradictions. Also, of course, all contradictions are false, so there are no true contradictions. But it's the only approach where contradicting yourself is not a cost. So Stuart Shapiro once put it nicely, you bite the bullet at the beginning and don't have to go up this hierarchy. He wasn't necessarily endorsing the approach, but he was at least appreciating the purity of it. So dialethism, it's not a solution to the paradoxes the way the other ones are. It doesn't make them go away. It more or less just accepts that they're there and they say what they seem to say. So it's more like an attempt to accept them and learn from them. And say, look, we discovered over 100 years ago that there's some kind of fixed point knot at the bottom of semantics and set theory and probably recursion theory and even arithmetic, as Russell and Gödel and Turing showed, and the way forward is to just take this part as part of logic and mathematics and study it and use it rather than try to untie it. if that makes sense, and I'm just going to have to leave that as a conditional for now, because we could argue for a whole semester about whether that was actually a good decision. But if conditionally that's the way to go, and this approach is going to be rationally coherent, then you need to have some accompanying paraconsistent logical system. So you say, all right, I'm going to accept their true contradictions. That doesn't mean that I'm just going to go off the deep end and accept that everything is true. This is still an attempt to remain scientific and not become some kind of mystic. So I'll call the paraconsistency thesis the claim that not everything is true, even if some contradictions are. That's the whole point of using a paraconsistent logic, is we take as our fundamental baseline condition for the precondition for rationality, some kind of Kantian transcendental deduction, that not everything is true, even if some contradiction turned out to be true. And if that's gonna work, then we'll have to go back and set up notions of truth and satisfaction and validity and provability, the kind of underlying components of any logical theory and mathematical theory that will deliver results without over-delivering. And that's the game. And hopefully I don't have to convince anybody that not everything is true. That's, we can all agree on that. If everything were true, we don't need to be here, because it's already true that you've got your PhD and your refrigerator is full of gold and you can fly and you're going to live forever and 0 equals 1 and dare to dream. So putting together the two things that we've got, dialethic paraconsistency says some, but not all contradictions are true. And we're going to pursue that. The idea is that to escape revenge and maintain the self-styled status as the only approach that escapes revenge, paraconsistency's got to set up its own framework. And it's got to do so in a way that does not backtrack on the idea, right? I just kind of accused all the other approaches to the paradoxes of in some way violating their own protocol statements or contradicting themselves at the meta level or undermining themselves. So if the approach that I'm sketching here is going to do better, we can't suddenly resort back to classical logic one step up, because that would be to commit the same fallacy or have the same kind of revenge problem that everybody else has. And you could say, look, well, it's the same problem everybody else has. I'm no worse off. And philosophers are always doing that. They're saying, well, that's not my problem. That's everybody's problem. Well, okay, if it's everybody's problem, it's also my problem. And let's deal with it. Okay, so here's Stuart saying, an important advantage, perhaps the major advantage of the program, is that there is no need for a separate meta language. So how to do this? Let's have a look. And we'll particularly focus on the role of negation in truth, validity, and proof. Whoa, okay. All right, so to do this, we first need to have some kind of logical machinery in the background that allows us to set up formal, precise notions of truth and proof and validity. So I'm not going to make much of the choice of logic. There are many paraconsistent logics and many choices one can make of which ones to use. For today, I'm going to invoke a logic called DLQ, which stands for dialethic logic with quantifiers, that was first put forward by Routley and Meyer in the 1970s in the Journal of Soviet Studies, and has been studied extensively by people like Ross Brady, who has a book called Universal Logic from 2006. So this is a relevant logic. Relevant logics require there to be a connection between the antecedent and consequent of a conditional, where the antecedent really gives you the consequent. So relevant logics are naturally paraconsistent because ex falso quod libet or explosion is irrelevant. You go from some arbitrary contradiction to some other totally unrelated thing is irrelevant. So relevant logics are natural fits for paraconsistency. They have their costs too, but this one's kind of nice. So there's a conditional. The conditional you can see in rule 1 down below obeys modus ponens. That's a point of some contention among paraconsistent logicians, but I think modus ponens is probably a good thing for a conditional to do. It does other good stuff, like it obeys identity and transitivity, and you've got connectives, conjunction that detaches in the usual sort of way and introduces in the usual sort of way, and there's distribution. There's a negation, the double negation eliminates and introduces and contraposes. And number 9 there, just to make very explicit, we have the law of excluded middle. So A or not A is true. So we're going to pursue the idea that there might be gluts, but no gaps. Other people pursue the idea that there's gaps, but no gluts. So let's look at the symmetric case. And this quantifier is around. And we'll also have this kind of useful rule that if you have A and the negation of B, that's sufficient for the negation of a conditional, though not vice versa. So that's the counterexample rule. And again, the idea is just this logic does a lot of familiar stuff. It's strong enough to get some results, but is not so strong as to collapse in the face of inconsistency. So that's what I'm going to have in the background. And what's really appealing about this, and the reason, one of the main reasons for selecting this one, is because on top of it, to do mathematics, we can then add to extend just the first order language with identity, set membership, and a set term binding operator, and add to it full naive comprehension. Which says that for any property at all, or for any formula at all, there's a set of things that satisfy that property. So X is a member of the A's, just in case X is an A, or even without the X, it can just be A, which people have probably told you is an untenable assumption because it leads to things like Russell's paradox. So that's why it's called naive comprehension. It definitely does lead to certain contradictions, but otherwise it's intuitively very appealing and arguably still what people are using when they work with sets in the back of their minds, unless you audit them and then they say, no, I wasn't. That's we can talk about that too. So it's comprehension. There's an axiom of extensionality that says sets are equal when they have the same members, as we discussed right before the talk started. Coextensive things are treated as identical. Coextensive in the sense of having the same members with this strong relevant connection. So if being a member of X really relevantly implies being a member of the Y's, then X is identical to the Y's. But the relevant arrow there rules out kind of accidental extensional overlaps, because the two things have to kind of mean the same thing. So that's why we can get away with extensionality. And with all this, there's also substitution, which apparently is also controversial sometimes, that if two things are identical, then anything you can say about the one, you can say about the other. Once you've got that under your belt, you can develop very basic widgets like singletons. And with singletons, you can then give the standard definition of ordered pairs, and prove the law of ordered pairs. And from that, you can use to define Cartesian products and subsets of Cartesian products, which we call relations, and special kinds of relations, which we call functions, and also have some kind of indexing set. All we'll need for today is the natural numbers, 0, 1, 2, that obey some kind of induction. And like I said, there are many choices of paraconsistent logic, and concomitantly, there are many choices of paraconsistent set theory that you sit on top of the logic, and they go in kind of different ways. Some of them are more truth functional than others, but I'm picking this one as the background choice for today. All right. I think we're now ready to move to truth and untruth. I guess I'll just pause again and give you the audience a minute if there's anything. I've said a lot of stuff already, so if there's anything I've said so far that you want to stop and query. Super. Truth. So I said we're going to compare moderate and radical approaches. So first, let's look at the standard or moderate way of presenting a glut-friendly paraconsistent system, which we find people like Graham Priest and J.C. Beale doing. I guess it's a sign of how far gone I am that I consider Priest to be a moderate paraconsistent logician. He takes a very kind of conservative approach to presenting these things, and the whole approach is based on distinguishing falsity from untruth. So just to the main idea will be, classically we have the idea that there's truth and falsity, and one is the mirror image of the other. And the idea of the moderate way of doing things is we could allow there to be contradictions or inconsistency by making them independent, by making truth and falsity to some extent independent. So just because something's false doesn't mean it's automatically not true. And that's how you could have a contradiction. Or just because something's not true doesn't mean it's automatically false. So the two properties of truth and falsity are permitted to float free from each other a little bit. And that's why it's possible to give a classical representation of inconsistencies, because you sort of say, well, we've got these two so just to kind of parody the idea, we've got these two properties like being red and being in my refrigerator, and sometimes there's red things that are also in my refrigerator, and there's no problem with that because redness and being in the refrigerator don't contradict. So truth and falsity are made to no longer contradict each other, and that's how you can set up, for example, a model for first order LP, that's Priest's logic of paradox, which was anticipated by Asenio in the 60s with identity. All right, some logic. So we'll set up, so we're going to just have a standard language for first order logic with identity in the background. So there'll be variables x, y, z, and constants a, b, c, predicate symbols of any arity greater than 0. So we don't have any constants in the language, although it will be possible later to define a bottom constant out of the set theory. Look, somebody's raised their hand.
Yeah.
Stop it. Yeah.
So I had a quick question. So you had stated that the logic you're using does accommodate A or not A. So that kind of bivalence. And I was wondering how that squares with what you said a moment ago, that falsity does not imply not true.
Yes, good question. So we're going to come to this. We're going to distinguish, right? Falsity is going to mean truth of negation. So to be false means that the negation, if A is false, the negation of A is true. So bivalence in the logic that I just flicked past you says for any A, either A is true or A is false. So truth and falsity will be exhaustive, but that doesn't mean that not false implies that true implies not false. So I'll blast to my Venn diagram here and then come back, right? So the kind of picture here, the picture is that you've got there's a plus over there, that's the true things, and the minus on the other side, that's the false things. And the idea is it's exhaustive in that everything has to fall into one of those two circles, but the two circles can have an overlap that's not empty. So that's where the A and not A might end up. So that's how you can have bivalence without, but you could see that if something might be false without being untrue, because if it's false, it could be in this intersect, and that if it's in the intersection, it's not untrue, it's also true.
Okay.
Does that answer the question?
Yes, thanks.
Yes, I mean, I'm introducing this as somewhat problematic, and we'll come back to why it's problematic, but let's just see how it gets set up. Okay, so standard language with connectives. Notably, we're only going to be looking at models for LP, and LP does not have a conditional. So the logic that I'm using in the background has a real robust conditional, LP just has conjunction, disjunction, negation. So we're just going to focus on that as the logic that we're setting up the theory of, because these real conditionals are harder to work with, and we'd need more time to talk about that. So there's variables and terms and formulas and everything. This is all, you could find this on page 1 of any classical logic textbook as well. This is the language of first-order logic. A model is going to consist of a non-empty domain and an interpretation that interprets constants from the language as members of the domain. And this is the truth-falsity trick. So for n-place predicate f, there's going to be 2 separate interpretations of f. The things that are f, so we'll have a plus, and the things that are provably not f, the things that are truly f and the things that are falsely f, if you want. So the minus isn't failing to be f, it's that it's not f. And we'll interpret those as subsets of the domain that are, for n-place predicates, runs of variables and n tuples out of the domain that get picked out as the f things. So we will assume bivalence, that the things that are f and the things that aren't f exhaust the domain, but we don't insist that the intersection of the plus f's and the minus f's is empty. And that's the picture that we'll get to in a couple of slides. Similarly with identity, we will insist that everything is identical to itself. So all the tuples where, all the pairs where both coordinates are the same thing, that interprets identity, but we don't necessarily insist that there aren't non-identical things, non-self-identical things. So everything is self-identical, but also maybe some things might be not self-identical. And that's all you need to do to set things up in the background, is kind of have, if you like, the extension of f and the anti-extension of f, and think of those as 2 different sets. The things that are red and the things that aren't red, and those are kind of 2 separate properties that maybe happen to have something to do with each other, but not necessarily. So then we have evaluation that assigns truth values to formulas, and it does it in a relational way. So if this screen looks like a lot of symbols, you just squint at it, and if the set memberships there were equal signs, this would be standard classical logic. So all we're doing is relaxing that a little bit and saying these 2 truth values, true and false, could be among the values a formula takes. So true is in the interpretation of f if and only if the things that are predicated of f really are in the extension of f, and it's false of f if the things are in the anti-extension of f. A negation is true if its negand is at least false. So one way to read these is at least. So the negation is at least true if the negand is at least false. And since this is just a membership relation, there's nothing about that that rules out that also another truth value gets in there. A negation is false if its negand is true. And similarly for all the other connectives, the same stuff that you learned, except relaxed a little bit to be relational. This is called, this trick is due to Dunn, it's Dunn semantics, or the 2-valued relational Dunn semantics for, really this is just FDE, but once we impose no gaps over it, it becomes Dunn semantics for LP. So conjunctions are true if both conjuncts are. They're false if one of the conjuncts is. It's true and false if both conjuncts are true and also one of the conjuncts is false, etc. Easy. Natural, easiest thing in the world. If you wanted to simplify that, if the membership relation that we just looked at is from classical set theory, then the above semantics that we just looked at could also be thought of as having a 3-valued presentation, because there's really, only three possibilities once we rule out gaps. Either a formula is only true, so that means it gets to be true, but it's not false. It's false, but it's not true, or it's both true and false. And the fourth possibility, where it's neither, is being excluded here because we assume bivalence. And that's assuming the background set theory or the background relation, truth relation, is consistent. So the standard approach doesn't want the contradictions inside the language getting out and spilling all over the meta theory and saying true is in A and also true is not in A. Because if that were to happen, well, to prevent that from happening, and I think this goes to the question that the black hole asked me, Arand, we have to, if you want to keep the membership relation consistent, you do have to reject one of these two directions, which we'll call exhaustion and exclusion. Exhaustion says if something is untrue, then it's false. So untruth implies falsity. If truth is not a member of the values of A, then truth must be a member of the negation of A, because falsity means truth of negation. We will have that, or even so in the LP setup, we're going to keep exhaustion because we want bivalence. So we'll say if something's not in the truth circle, then it must be in the falsity circle, because it must be in one of those two circles. But to keep, so if you want to keep that, then, and you want to keep the membership relation consistent, then you'll have to drop exclusion, which says, well, if A is false, if its negation is true, then it's not untrue. If there's truth in the negation of A, then it's not the case that the negand doesn't get truth. So that would be saying, and classical logic has both of these conditions. If you impose both these conditions, you just get classical logic back, which says that you can't have both those things. Actually, that's a bit too quick. I don't think you get classical logic back straight away, but you would get contradictions at the meta level. So looking at this, Priest says, I want to keep exhaustion because I want to keep bivalence, or the law of excluded middle, but we should drop exclusion because Priest has this principle that it's like Occam's razor, that one should not multiply contradictions beyond necessity. Maybe the liar paradox forces us to have contradictions, but we shouldn't go farther than that. But keeping both exhaustion and exclusion would let contradictions out into the meta level, and that's problematic, as we'll now see. Because on the other hand, if you have so that's the moderate approach. If you have a fully paraconsistent meta theory, there's no in principle problem with inconsistent set membership. In fact, you're going to have inconsistent set membership because the Russell set is a member of itself and not a member of itself, as your mother told you. So you could even, if the membership relation is from paraconsistent set theory, you could come back and say, look, what is all this truth and falsity are independent properties stuff? Truth and falsity contradict each other. That's what a contradiction is. So if A is true, then it's not false. And if it's false, then it's not true. And you could add those conditions to your semantics and restore kind of the connection between truth and falsity and adopt both exclusion and exhaustion, but in a paraconsistent framework, and let them contradict each other. And then excludes can itself be inconsistent. So you say, look, of course, the truth of A excludes the truth of not A, but also sometimes A and not A are both true. Because I said dialethism contradicts itself, and that's what it was packaged as, and that's what it should be when you take it out of the package. So that's the picture, we saw that. And similarly, if you want to keep the theory consistent, you'll have to drop one of exhaustion or exclusion for the interpretation of predicates and reject that untruth implies falsity. But arguably, if you're a serious dialethic paraconsistent logician, you might think that that's exactly what you want, that there should be contradictory interactions. Like if something is truly F, then it's not F. Right? If something's in the extension of the F's, then it shouldn't be in the anti-extension of the F's. What's this extension anti-extension stuff? Like either you're F or you're not F. This has the cost of introducing significant noise into the models, but I think part of the aim was to listen to the noise. So what happens if we essentially drop off the pluses and the minuses and go back to a more natural connection between truth and falsity? So I've complained about that. Then we return to this picture where there's just the F's and the not F's. And also sometimes something could be both F and not F if you want to know where that is. Maybe it's sitting on the boundary of the two, but there aren't these two separate or independent properties. You can just say untrue is false. And again, the motivation for that really is not just naturalness, but a worry that invoking a consistent distinction between falsity and untruth is essentially trying to return to classical logic at the meta level and terminally threatening to undermine the program by taking back what you said. Like the plan was we're going to deal with the paradoxes by dropping classical logic. And then if you go one step up and say, well, I'm really still using classical logic, then you're not doing what you said and risking revenge. Essentially, if falsity and untruth are separate things, then you're saying there could be true contradictions by saying that truth and falsity don't contradict anymore. And that's problematic, I think. So what's a true contradiction if truth and falsity don't contradict? That's a homework assignment. So we can now go back and redo the models from our fully robustly radical standpoint and listen to the noise. And this is really easy to do because it looks exactly like models for first order logic, standard first order logic. We just have a model with a domain and an interpretation, and we interpret predicates as subsets of the domain. And we say that the interpretation is fully exhaustive and fully exclusive in the sense with this negation now is paraconsistent negation. So there's nothing in the intersection of the F's and the not F's. There's nothing that's both F and not F. And that's basically just reflecting that in LP, the law of non-contradiction is valid. You'll get as a theorem, it's not the case that A and not A is always at least true. If I had a whiteboard, I'd write. We've got the law of excluded middle, A or not A, and we've got all the De Morgan laws. So if A or not A is valid, then we De Morgan it, and it's not the case that A and not A is also going to be valid. It also sometimes has counterexamples, but it's also valid. So the domain is exclusive and exhaustive and also sometimes not exclusive. Similarly, identity can be interpreted as identity, and you can even say nothing is not self-identical, even if also sometimes things are not self-identical, and everything's fine. This multiplies contradictions as necessary. Unfortunately, nothing is ever without difficulty in philosophy or life. Making these arrangements is not so difficult. It becomes more complicated when we apply this to validity, which I'll show you a problem with now. And then maybe I'll say something about proof, although I see we're running up to the hour mark. So it depends how much you want to listen to me and what you want to talk. So that's truth. That was just truth and untruth. Logic is not just about truth and untruth. We need a notion of validity. This is also fairly straightforward. So we've got models. A sentence is true in a model when the interpretation in the model makes it true. There it is. A sentence is a theorem when it's true in every model, and an argument is valid if every model that makes the premises true makes the conclusion true, as I tell my students. An argument then is invalid if there's a counterexample to it. So if there's some model that makes all the premises true, but makes the conclusion untrue, then the argument's invalid. And that's the way you show that, for example, ex falso quodlibet is invalid. You provide some model that can make some contradiction, like P and not P, true, but utterly fails to make some other thing B, Q, or whatever, true. So that's how invalidity works. So it's tempting to put the pluses and the minuses back on the model satisfaction relation, but you don't have to. The dialethist can just say models make things true when they're true and make negations true when they're false. And again, this is the idea that we saw a minute ago, that you don't need these pluses and minuses. You can just have the, if you like, the pluses and minuses as the external paraconsistent negation over the theory. So the models always make A true or make the negation of A true, and never both, and sometimes both, and that's that. Fine. Okay, but I said this does introduce significant noise, and it's not just the noise that I just made, it gets noisier. In the language of LP, for any proposition or any formula at all, it's always been known, going back to Priest's paper in 1979, it's always been known that just in the language of LP, with conjunction, disjunction, negation, that there's an interpretation that makes every sentence both true and false. That the negation, it's purposefully set up to be more permissive. So just the syntax of conjunction, disjunction, negation never rules out an interpretation that makes every formula both true and false, which could be concerning or not, depending on what concerns you. So this is just, right, P gets into this valuation if it gets assigned Z, and Z is either false or true. Since false is identical to itself, P gets assigned Z, false, and since true is identical to itself, that makes this disjunction true. So P also gets assigned true. So there's a way to make everything both true and false, and Priest knows about that, and he says, you know, so that it's kind of a way of saying, like, well, maybe everything is possible in some sense, or there's a trivial world somewhere. Okay, that's fine. That's fine. Everybody knows about that. But let's amp it up and use our background paraconsistent meta theory and say, well, what about this assignment? We know in the background meta theory that there's going to be some provable contradictions. So let's let math fractor P stand for some proven contradiction, like the Russell set is a member of itself, which is both true and false. So we'll take the same assignment that we just had, but sort of modulate it by a true contradiction, so that this is now a conjunction with the same conjunct as before plus P. So since P is true, all the same truth values we just saw before get assigned. But also, since P is false, this conjunction is false. So also all of those truth values don't get assigned, because this conditional contraposes, and if you have a false conjunct over here, then this membership relation is false over there. So we'll get for every single sentence that P is true in this interpretation, just in this interpretation. This is one interpretation. P is true in it, P is false in it, P is untrue in it, and P is unfalse in it. And that's kind of what you should expect to happen if I said truth and, well, untruth and falsity are the same thing. So if you have that P is false, then it's also untrue. And if it's true, it's also unfalse. This is one model that makes everything both true and untrue. That makes any A both true and untrue. And that, by the definition of invalidity that I flicked by you before, makes every argument invalid, because there's an assignment that makes the so this is just identity. There's an assignment that makes the antecedent true and makes the consequent untrue. So A implies the argument from A to A is invalid. It's still valid, So this doesn't make everything valid, but it makes everything invalid. And this has been observed in a critical way by people like Diederik Battens and Gareth Young. And it strikes me as too big a bullet to bite. I've just spent the last hour basically casually biting maybe every bullet there is, but I think this is not good. Why? Well, this is why I did so much methodological setup at the beginning. Look, dialethism does contradict itself. So you might say, look, you're a dialethist, so everything's invalid, and also some things are not invalid, and what's your problem? This is not, dialethism is not a get out of jail free card to just accept any old problem that comes along. In fact, it's like the opposite. It's saying sometimes problems come along that are so hard that I'm going to work really, really hard to be paraconsistent and still maintain things like naive set theory, even though the Russell set is both a member of itself and not. If you just say, look, I'm paraconsistent about some things, so whenever a problem comes along, I'm going to blow it off, that would be a bad methodological slide that's pretty close to just ex falso, like since I allow and admit some contradiction somewhere, I could just allow them anywhere. I think that's self-defeating and incoherent. I think that paraconsistency is a tool that comes in after we've already decided not to be self-defeating. That's the paraconsistency thesis that I thesised at you previously. And by comparison, if you're a classical logician, you don't say, I am consistent because I use classical logic. If it weren't for classical logic, I would just be doing any old thing. You say, I endorse or commit to classical logic because I antecedently endorse consistency. The logic expresses my commitments rather than the other way around. And I'm going to say the same thing for paraconsistency. We begin with a commitment to be coherent and do all this work rather than expect the formalism to just do it for us. And so to here, I think that all arguments being invalid has let everything fall apart. And so this can be prevented by introducing or defining. So with the set theory, one can define a bottom constant or a falsity constant or an absurdity constant or a church constant. It has many names, but it's an upside down T. This can be defined set theoretically as the sentence, for every x and for every y, x is a member of y. So every two things are members of each other. If you assume that and naive comprehension, then you get this proposition that would be explosive and can be absolutely false. So paraconsistency is the thesis that at least one proposition is utterly false, even if some contradictions are true. Then we can add to our requirements on what it takes to be a model that no model makes the sentence true. So we add the sentence to the language, or have the sentence in the language, and say the only way you get to be a model is if you at least make one thing, fail to make one thing true. And we'll say that by saying that if bottom in the language got to be made true, then that would make bottom true in real life. And again, if bottom were true in real life, then everything would be true. And again, we could go home and look at all the gold that we have buried in the backyard because everything is true. So it's a little bit ad hoc in the sense that we're piloting in an extra falsity constant and insisting that now models can't make that true in the sense of if it made it true, then absurdity would follow. But I also think it's not really ad hoc given the philosophical setup that preceded, and also because the bottom constant is already available from the set theory. So it's not like I artificially imported it. It was kind of already there. And if we do that, then there is no coherent, trivial interpretation. That very, very noisy interpretation that I showed you before stops being an interpretation. So that accepts a lot of noise, but not the ultimate amount of noise. Methodologically, how one goes about deciding when is it too much noise, maybe we can talk about in the Q&A. So I see in the chat I'm allowed to go over a little bit. I am at the hour, and I don't want to try your patience too much. Should I flick through the last section, or is that good? Because we could just stop there.
Well, either way, it's fine with me. I'm having a great time listening to this. So
Insanity. All right, I'll talk for a few more minutes, and then we can take a break. So I just want to. So that we looked at truth and untruth. We looked at then setting up validity and invalidity and the invalidity problem. This I'll say again, this is a fairly drastic solution, right? So this doesn't just bring in a sentence that is absolutely untrue. It brings in a sentence that's necessarily untrue. It's a single sentence that cannot be true in any model. There'd probably be a more careful way to do this, where you just insist that to be a model must fail to make at least one sentence true, but it could be a different sentence in each model. That would probably be a more natural thing to say. This is sort of the global from the top, God told me that bottom can never be true. So maybe it's a placeholder for a slightly more fine-grained solution that someone else can do. Proofs. So that's all been semantics so far. Let's look at derivations just briefly. An argument's proof theoretically valid if you've got some proof system where you can derive the conclusion from the premises. And this puts truth and falsity to one side and just talks about syntactic or proof theoretic operations. I give you some premises and you give you some rules, and you crank through the premises and get to a conclusion using the rules. And that's much closer to something that, say, a computer could just do without knowing what's going on. That's what these things were for. They were meant to be decision procedures. So arguments are valid if there's a sequence leading from the premises to the conclusions, and they're invalid if there is no such sequence. And normally speaking, soundness and completeness theorems connect up proof theory to model theory and say, well, how do I, give me some premises, how do I know I'll never be able to derive a conclusion? Because if you just sit around trying to derive it, you might fail 50 times, but on the 51st time, you might succeed. Say, well, luckily we have soundness and completeness that tells us that there's a counterexample in the model theory, so that tells you to stop trying to prove it. That doesn't work quite as well here, but we'll just blast through that and just say, look, if you're talking about inconsistent meta theory, it's one thing to say all this semantic stuff, but now you're talking about inconsistent derivations, and it starts to get harder to see what you're even talking about. If you have, right, I gave you some premises and you cranked through some rules and I proved B, what would it mean to prove and not prove B? That's something I can sit and do on my blackboard with my hands. And what? And Shapiro has a paper about inconsistent arithmetic from 2002 in mind, making more or less this point. I think he has a follow-up as well in this Festschrift for Grand Prix that came out in 2019. Well, let me just float something. There is reason to think that the proof relation is inconsistent, and this has actually been one of the motivating things for dialethism and paraconsistency in this mold, going back to Priest 1979. So if you go back to Priest's Logic of Paradox paper, he does not motivate dialethism with the liar sentence. I'm not sure if the liar sentence is even mentioned in that paper. Maybe it is. But his main argument is from Gödel's incompleteness theorem. His main argument is that the Gödel theorem appears to prove that mathematics and arithmetic are inconsistent. And the reason for that is that Gödel's coding device gives us some way to arithmetically express a sentence that we can see says, this sentence is unprovable, not untrue, but unprovable. And if we kind of think about it and reason about it in a natural way, one finds that it is both true and false. So there's a sentence that seems to predict that there should be something that is both provable and not provable, which means there is both a proof of it and not proof of it. And okay, that's sort of a prediction. And I don't know, you could take it as like dark matter, like the equations say there must be something out there, and to make it balance, I guess they must be out there, and I don't know what it looks like. But what would it look like? And so this is going to go back to what I started with the ordinariness hypothesis and the non-classicality is non-classical hypothesis. Again, it might be tempting to say, oh, well, it's a proof relation with some kind of Mobius strips or quantum, maybe quantum. That's always a good thing to say. I have suggested that the way to go at this stuff is to demystify the problem and adopt the attitude that what we're seeking is new, but it's not new because of like some discovery of new technology or some way that Turing machines can be turned upside down, but new ways of thinking about what we've already got in standard technology. How do we do that? A proof is a sequence. A sequence is a tuple. That's a tuple. There's a tuple. It leads, if there is a proof of, say, the Gödel sentence G that says the sentence is not provable, it looks like that. It looks like a sequence of formulas ending in G. And I said at the beginning, we have a background set theory that can define ordered pairs and ordered tuples, and we're imagining this tuple built out of that set theory. All right, so there it is. If it's provable, then it looks like that. If there's no proof of G, well, then there is no sequence ending with G with properties like that. How could that be? Especially if we're looking at one. Let's just look at a very toy example of a tuple with two things in it, A0 and A1. So that's up there at the top. That's a very short proof from A0 to A1. If we set theoretically dissect this using the Werner-Kuratowski definition of ordered pairs, it breaks apart like that. You can do that as just an exercise in applying the definition. Right? This is there's nothing particularly special about this definition except that it delivers the law of ordered pairs. Suppose, so right, it's composed of, ultimately you get down to a set of things that are identical to A0 or A1. Suppose that A0 was a non-self-identical object. How could that be? Well, we know that there are some non-self-identical objects because the Russell set is a member of itself and not a member of itself. The axiom of extensionality says that two sets are identical when they have all the same members, and they are not identical when they differ from each other with respect to membership. So if this set has a member that the other set does not have, then they're not the same set. The Russell set has itself in it and does not have itself in it, so the Russell set is not identical to itself. It's also identical to itself, but it's not identical to itself. Sure. Just suppose that there's things like that in the background. So suppose we had some A0 that was not identical to itself. Then A0 would be in its own singleton because it's identical to itself. It would also not be in its own singleton because it's not identical to itself. That means its singleton is not identical to its singleton because the singleton differs from itself with respect to membership. And that means, once we go and apply it onto these equal signs, that this sequence, this very short little tuple, is not identical to itself either. So if mathfrak A is a sequence containing a non-self-identical object, then the sequence itself becomes not self-identical. And that's going to generalize to any tuple, any finite tuple containing a non-self-identical A. Then we invoke the straightforward non-self-identity lemma, which says, look, if something's not self-identical, then it's not identical to anything. So if A is not identical to A, then it's, for all Y, it's not identical to Y, and that's just proven by substitution. Well, if Y were identical to A, it would have every property that A has. A has the property of not being identical to A, so then Y is not identical to A either. Oh, that should be an A, sorry. Y is not identical to A. And that, I think that makes sense. That non-self-identical things are provably not identical to anything else. That means if we had some sequence, so let's go back to this proof of the Gödel sentence. And if the Gödel sentence were non-self-identical, right? The Gödel sentence says this sentence is not provable. It's both provable and not. So let's say that that led to it being non-self-identical. Then this sequence would also not be a sequence, because the whole sequence would not be equal to itself. And indeed, you could generalize and say there is no Y that is a sequence ending in G. So there is a sequence ending in G, but also because of the non-self-identicality of G, there is no sequence ending in G. So what does an inconsistent proof look like? It looks like a proof that ends with an inconsistent object. So if you're wondering what could it possibly mean to both prove something and not prove something, this is a way of reducing the problem, saying it means you've proved it and you've proved something in your proof was self-inconsistent. So also you didn't prove it, because proofs with self-inconsistent things are not proofs. That leaves us with the question of what does an inconsistent object look like, which I will leave as homework. All right, conclusion. Revision. You're saying very revisionary and weird stuff. I guess it's a Friday afternoon in Ohio, so it's all right. What happens? Well, I don't really know what happens if we go that way. That way lies uncharted waters, but some of us would not be where we are today if people had not at various times set sail into uncharted waters. That's what people do. That's called research. At the end of the day, I started with the inconsistent mathematics program. If at the end of the day, you're not persuaded that inconsistent mathematics or this whole thing might in some sense be true, and so in a basic logical sense, at odds with classical mathematics, it is not clear to me, at least, what the project here even is. So I eventually get confused what weak paraconsistentists or moderate paraconsistentists are even up to. Why do all this weird stuff if you don't think that it stands some chance of being correct? Why do something so difficult, unappreciated, and weird when compared to its classical counterpart, unless you think it's true? If you're persuaded to think that some of this inconsistent mathematics stuff might be true, then revision might be less reassuring than maybe it's sometimes the paraconsistent stuff is marketed as, right? This story of, look, you can just keep all of your classical stuff, but sometimes we extend into the non-classical. This is shaking that story and saying once you extend it to the non-classical, it's going to bleed back in and everything's up for revision, everything's up for grabs. And that might be less reassuring than what you meant to sign up for, but pursuing theories for their truth, as Nietzsche taught us, is not always reassuring. If you are persuaded to pursue this, it might not be reassuring, and there's no real reassurance otherwise. So I think if I've pointed to some, especially with the invalidity problem, I've pointed to some very serious problems in setting things up paraconsistently. I've only waved my hands at a possible way of thinking about what inconsistent proofs, or down the line, what inconsistent computability might ever look like. I'm not saying it absolutely can be done, but I'm saying the future for paraconsistency, as I see it, is to follow out a more radical project. It's committed to finding new rules, overturning old ones, and sometimes risks literally not being understood by anyone because you start saying things that go beyond what can be classically represented or accepted. And that's the plan. And maybe it'll work and maybe it won't. But conservative projects that are subsumed under standard mathematics will always remain on safe and previously trodden ground. And that's safe and previously trodden. That's why I said at the beginning, if you want to make sure you get a result for your PhD, do that. The more radical approach is to embark on a project that is not safe. It might fail. That's what makes it research. And that is what holds out the chance of achieving something genuinely new. So thank you for letting me go a bit over and your patience in listening. And if the world as we know it behaves classically, there will never be a satisfactory answer to what the paraconsistent bits are like. If the world as we know it behaves according to paraconsistent logic, there's a simple answer to what the paraconsistent bits look like. So I'm recommending if we start looking at the non-classical as ordinary and the ordinary is non-classical, then the real hard work can begin. Propaganda finished. Thank you very much.